Let's get going. So thank you everyone for coming to my talk. My name is Noel Welsh. I am a consultant at Underscore. Underscore is a Scala consulting company based in the UK with offices in the US and Australia. I just want to let you know we recently, as in a couple of days ago, made all of our books free. So if you're interested in any of our material on Scala, going from very basics up to advanced stuff, like your type classes and monads and stuff, you can go to our website and you can find any of our books available there, download, grab a copy. I want to start with a little bit of audience participation so I can see who I'm going to offend in this talk. So hopefully I offend no one, but let's have a quick show of hands. Let's have a show of hands if you are from the US. That's gonna be a friend. And leave your hand up if you're a fan of Donald Trump. Okay, good stuff. What about if you're from the UK? And leave your hand up if you're a fan of leaving the European Union. All right, good. Right, we should be safe then. We can get going. So this is a talk about church and state. And many people believe that church and state do not go very well together. But I am from the UK, and in the UK, we have a union of church and state. This is the Queen, the good ship QE2, and she is both the head of the Church of England and the head of state. And I think things work quite well there. We have a national health service, we have a social security system that works reasonably well. I think uniting church and state seems to work okay, though we do have the occasional unfortunate side effect. So this talk is really about uniting church and state and avoiding unfortunate side effects along the way. But I should clarify that when I'm talking about church, what I actually mean is the work of this chap, Alonzo Church, who invented the lambda calculus, amongst other things. And when I'm talking about state, what I really mean is sort of OO imperative style programming, here with Alan Kay, inventor of Smalltalk. And when you mix those two together, unite church and state in the programming world, what do you get? Well, obviously, that handsome fellow. Okay, so Scala has these object-oriented and these functional programming features. It's touted as an object functional language. But what does that really mean? I don't think it's enough just to have the language features together. You really need some kind of coherent way of using them. And when we look at how Scala is used in the real world, I think we see a real kind of schism between people who use Scala in a sort of OO ways, maybe a better Java, and we see the people who go more towards the functional side, and they tend to avoid the OO parts of the language. And I'd probably say I'm definitely in the functional side. I'm not saying it's right or wrong, I'm just sort of revealing my own biases here. So what we need is some kind of conceptual model, some kind of mental model that's going to actually unite these different programming paradigms and then give us a consistent way of thinking about them so we can truly use the power of the OO and the FP features in Scala. So what I want to show you today is the church encoding as a way of achieving this unity, uniting the FP and the OO side, the mental models, and then we can fully leverage Scala's features. So the claims I'm going to make. Firstly, that FP and OO make different trade-offs. Then I want to show that FP and OO are related by the church encoding. So the church encoding is this tool that's going to allow us to go from FP style to OO style, and there's going to be an inverse called reification, which is going to allow us to go the other way. Once we've got this established, I hope I can show you that we can think of code think of our system design in one consistent model and then choose the FP or the OO representation depending on the trade-offs we want to make. So we can achieve this conceptual unity that I think is missing. Then I want to show you this is actually useful, not just it's a nice kind of theoretical babble. And I'll give an example of a case study we worked on in a time series analysis system where we made use of this to achieve some performance optimizations. And finally, I want to talk about things that are so hot right now, free monad and tagless final, or finally tagless, sometimes interpreters. You may have heard people talking about these in other talks or in other areas. And I want to show how we can use the church encoding again as a tool to unify these concepts. So again, reducing the number of models we need and freeing up space in our heads for other things, which is good. So I better start off by defining some terms. I'm going to show a way of implementing a very simple system with what I consider to be classical OO and FP techniques. So these are the kind of things you might have done in Java back in the early 90s, or in sort of ML if you were into functional programming at the time. So very, very basic FP OO, nothing fancy going on here. And I want to implement a calculator. Again, it's a very simple example. It's just designed to be easy enough for everybody to grasp what's going on. I'm not intending to show anything of great depth here. I don't want people to get lost. So if we implement a calculator in a classic OO style, we might end up with something like this. Like I said, very simple implementation. You have a bunch of methods, and they do what they say they're going to do. So you add together doubles, so on. Not very interesting. The way you'd use it, create your calculator instance, and you can import it in Scala. It makes the slides a little bit shorter, the code a little bit shorter on the slides, and away you go. Call the methods, do the things. Very simple stuff. Now, what I want to focus on here is the extensibility we have here. So we see in the OO style, if we want to add new operations, we can do that fairly easily. So for example, we want to add some trig operations like sine and cos. We can just subtype the calculator and add them in, like that, new methods, using a bit of inheritance. So that's very easy to achieve, that type of extensibility. If we want to add what I call actions, that's a lot harder. So for example, what if we wanted to change our calculator to compute with big decimal, because we're maybe working with currency, we need some exact results. We have to change all of our existing code, because back in the calculator, we see there we're working with doubles. We'd have to go back and change all this code to be big decimal. The same if we want a pretty print expression, say, we want some kind of trace of what's going on, returning a string, we'd have to go and make a change to all of the code. So what we see here with OO style is that we can easily add new operators, methods. Inheritance allows us to do that very easily. But adding a new action, changing a return type, is something that requires a change to all of our existing code to achieve. Okay, let's look at the classic FP approach. So in classic FP, you're going to represent operations as data, something like this. So an algebraic data type, if you like your FP jargon, a sealed trait, a bunch of case classes, if you want to think of it just in terms of the Scala implementation. We have a lot of Scala noise here, these final case classes, but I'm sure you get the idea. And then what you would do is define some function that's going to process these. So in the kind of FP jargon, you might talk about this being an interpreter. And it could look like that, just a simple pattern match, structural recursion, again, if you like your FP jargon. And we just go through the different cases and do the appropriate thing, whatever it is we got to do. So that's reasonably straightforward. Now again, let's look at the extensibility we get from this. What we did with the OO style, adding those trig operations, we can't do now because we have a sealed trait. We can't add anything to that without going back and modifying that code. However, we can easily add new actions in this example. So let's say we want a pretty print. Well, that's straightforward to implement. There we go. It's got exactly the same structure as eval we saw earlier. So the conclusion here, we cannot easily add new operators, but we can easily add new actions or interpreters. Gives us an idea that we've got a bit of orthogonal extensibility going on here. So let's just summarize that, FP versus OO. You can see we have this. So the extensibility we get from OO is orthogonal, goes in different direction to the extensibility we get from FP. So this suggests that we could usefully combine the two to achieve extensibility in whichever direction is relevant for our problem. Okay, I'll talk a little bit about avoiding side effects here. So the terminology I'm using, just to make it clear, operations are what we want to do, and actions are how we want to do it, so the different, like evaluating, printing, and so on. And one of the sort of FP mantras is separate describing what you want to do from how you're actually going to do it. So this is what allows us to avoid side effects when we don't want them, because you describe what you want to happen, and then when you go and do it is when the side effects actually occur, and by separating your program into these two parts, you can keep the side effects out of the part where you're describing. So it basically boils down to, in the terminology I'm using here, separating the operations from the actions and making the side effects happen in the actions. So we'll be using this kind of framework to think about things. All right, let's check. Any questions about this bit? It's fairly important. Okay, good. So let's move on to the church encoding. So the church encoding is going to be a way to take us from FP style to OO style. And what we're going to do, so if we take the FP style code here, and I've just simplified it a bit here, removed a little bit of the noise, so you can just see more clearly the structure, and we compare it to the OO style, again, a little bit simplified, we'll see that they are very, very similar, really. And what's going on here is constructors have become method calls, and the operator type becomes the action type. So let's just wind back to that to have a look. You can see the constructors literal add, subtract, multiply, divide. They just become method calls there. And the the calc is becoming, goes to double. So operator goes to action. That's basically what's changed. So that is essentially the church encoding. It's a fairly simple thing. Like most things in functional programming, it's a simple idea wrapped up in a bunch of fancy words so you can look smart when you're talking about it to your friends. And as you can imagine, you can go the other way, turning methods into constructors and doing that type conversion. And that, of course, has a fancy name as well. The name is reification. Reifying means to make things that are abstract concrete, so to make sort of actions, methods into concrete data. Again, a fancy word for a simple idea. Very typical of functional programming. Remember those fancy words when you want to impress your friends, but maybe not when you want understanding. Okay, so this is the core of the idea. We can take FP style, we can turn it into OO style, we can take OO style, we can turn it into FP style, but then is this actually a useful thing to do? Let's have a look at it. So I want to talk about a case study example where we did use this in a real commercial system. And one thing I want to talk about in particular is performance. So there are different performance characteristics in the two encodings here. Particularly the FP style, you're creating this intermediate data structure. So we saw in the calculation example, you created that calculation tree, if you like, and you then walked over that tree and chose what you're going to do. So there's some extra memory allocation and there's a little extra pattern matching going on. So you're incurring some extra costs there. In contrast, the OO style performs the actions immediately. So it could be more performant, seems like it would be in a kind of straightforward machine model. We have this less allocation, so that'd be nice. So, the case study. Last year, we were engaged by Maana, enterprise knowledge startup based in Seattle, to develop a time series analysis system. So a little bit of background. A lot of Maana's customers, I'll give you background first on what they do, actually. They essentially collect knowledge, which maybe you can think of as data that's in large enterprises, different data silos, unite it all, and then give people a unified interface to search over this data. Now, a lot of their customers are big industrial people, so they have things like oil wells or wind turbines, and these things are monitored with loads and loads of sensors, hundreds of sensors, producing data all the time. And when things go wrong, it's typically very expensive. Like when your oil well, your pump in your oil well gets wedged, that's bad news. So it's very natural for them to want to be able to predict these kind of things. And the first step to predicting things is to analyze the data and try to look for patterns that suggest a fault is going to occur. So some of the requirements, one of the main requirements we had was we had to have sort of real-time analysis. I put real-time in quotes because it's not like a hard real-time system where you have to guarantee a particular response time. But we wanted to get response times analyzing low terabytes of data in a second or less. So we don't want Scala compiler time sort of response times. We don't want people to wander off and do something else. We want to get them pretty snappy feedback because when you're analyzing the data, you want to get results very quickly. Now, one of the nice things about time series is they have a well-defined order, right? We have, of course, that order by time. So time goes from beginning to the end. That's well-defined. And all of the algorithms respect this order. There are no time series analysis algorithms that I know of that work opposite to the arrow time or jump around in time. They all work from the beginning to the end, essentially. Sometimes you may restrict them to some subset of the data. And what this means is that the system we can think of as being like a stream processing system. It doesn't matter if the data is arriving in real time or maybe we pull it from disk. Because we're just interested in processing the data from beginning to end, we can think of it as basically being a streaming system like Spark Streaming or FS2 or Akka Streams or Monix, whatever. That's a reasonable working mental model for the system we build. I don't want to go into all the details here. Some of them are locked up under NDA, of course, and I think a lot of the details are irrelevant, but you can just think of it as a system that's just producing data over time. So the heart of these systems is you construct a directed acyclic graph that represents what you want to do. So you start with some inputs, and you may then have some transformations. So these would be things like map and zip in the kind of general case. In our specific case, we have time series specific things like convolution and filtering by time range and this type of thing. And then eventually you want to aggregate your intermediate data into some final result. That may be, for us, like a search over time series for a particular sequence, or more general systems, this will be maybe writing stuff to a database or something along those lines, or making a sale. All right. So we have a pool-based model, and what that means is you start off by the sink, the most downstream node, makes a request for data. So it says to its children, going upstream, give me some data, and they say to their children, going upstream, give me some data, and then these nodes respond with data. The data flows back down, it gets to the end, and the process repeats. So pool-based systems are very simple. You don't have to worry about back pressure. It just happens automatically because no request comes down for data until the data is processed. So very simple to reason about, quite simple to implement as well. One of the problems, though, is that you need control information. It's not just enough to send back the data. You have to send back some information about what's going on. So the cases that may exist are that, well, you have data, that's good, that's the usual case. You may have no more data. If you're reading from disk, you run out of data, you read everything there is to read, for example. You can get in situations where you need more data because some intermediate node, say, is filtering out things for a certain timestamp. So it's saying, I haven't got to the timestamp I'm interested in yet, so you need to keep on pulling data through the system until you get to that interesting timestamp. And you could hit an error. So at least 4 cases that you want to report when you're asking for that data going down. And we can model these in the usual way. Seal trait, it's algebraic data type, result, emit, wait, incomplete, or error. And now when we look at it, if the request goes down, give me some data, or give me a result, I should say, and then it comes back up, we're allocating a result. We allocate a result here to store the data if we have data, or to indicate the other conditions that are going on. And as this goes up, we can allocate another result, and we allocate a result again. So the problem here is we've got a lot of allocation. We are allocating both per node and per data element. And because usually there's a lot of data going through, that could be a lot of allocation. It's typical to process hundreds of millions of data items. So allocating hundreds of millions of these results sounds like a bad thing. So what are we going to do? Well, it's Lonzo Church to the rescue. We can use this tool of the church encoding. And the key insight here is that returning a result is the same as making a call to its church encoding, right? So there's not just the church encoding going on, we change returning something into calling something. And I'll talk about that a bit more later, but for now, the church encoding is the idea to focus on. So I'm going to call the church encoding a receiver, just because it's useful to have different names to distinguish these things. And you can see it is a straightforward church encoding of what we saw before for a result. I'll just go back to result. Maybe I won't. There we go. So emit waiting complete error, and of course the church encoding has emit waiting complete and error. Straightforward. So now that what the control flow looks like is we go for our request to data, goes back down as before, and now when it comes back, we're not returning results anymore, we're making calls to these receivers. So we call that receiver to say this is what happened, and the receiver then is responsible for doing whatever the sensible action is on the data it gets back. Okay. And the most important point here is because the action that a particular node takes is fixed, if it's a map node, for example, when it gets data, it does that mapping, you know, and generally if you get an error, then you just propagate the error back up, for example, and same if the stream is complete, then you just tell everyone it's complete, you don't have anything else to do. We can allocate one of these receivers per node, and we don't have any per element allocation. And because there are many more elements than nodes, we've got rid of a lot of allocation here. So that seems like it should be a good thing. And we have some benchmarks to bear that out. So, it's FP style. We have, on a simple benchmark I wrote, 530 milliseconds, and the church encoded, we're down to 387 milliseconds, 1.4 times faster. This code is all on GitHub. So if you go there, you will see an example implementation. This is where I got the benchmarks from. And there are a few other implementations there as well. It might be of interest if you want to see how these systems are built. So, fairly significant performance improvement from this simple transformation. I hope everyone agrees it's reasonably simple, and that the performance improvement is worth having. I think it is. What I want to get back to is this difference. We said returning a result is the same as calling a receiver. So there's another difference going on here, not just the church encoding, because returning is not the same as calling. Well, there is another program transformation. If we think of the church encoding as a program transformation that takes us from FP to OO style, and reification, the program transformation that goes back, well, this other program transformation called continuation passing style is something that transforms from returning values into calling values. And we can basically apply the CPS transform to do this change to our code. It's something that if you've ever had to write anything at stack safe, you might have done this CPS transform. It's not the most pleasant thing to do, it's true to say, but it's no harder than programming with callbacks. That's basically what it is. And if no programmers can do it, by golly, Scala programmers can do it as well. So, yeah. So a quick summary of what have we done. We had a system where we've done it's actually a partial church encoding, it's a partial CPS transform, and we've got a large performance improvement from it. So this is very important for our particular use case. We can avoid this allocation because we've got lots and lots and lots of little just doubles going through, basically. We've got to avoid boxing them, we've got to avoid the allocation. Very important for our system. So if you go to the GitHub repo, there are some examples of different ways you can use the transformation. There's a fully church encoded, fully continuation passing style encoded implementation, the partial one, which is much closer to the actual system we implemented. And the point I want to make with this is, well, there are 2 points really. One is that the church encoding and the CPS transform as well, if you have to do it, it's not an all or nothing thing. You can do it partially, you can do it completely. You can choose the point on that knob which is right for your system. And the other thing is, although there's no doubt that the code becomes a little bit uglier in some way, because there is a well-defined transformation from one bit code, say the direct style code to the CPS style code, and from the church to the FP style code. You can keep one mental model and you can do that transformation to get to whatever mental model, whatever code is easiest to work with. So that you may not actually do the transformation in the code, you can sort of do the transformation in your head to work out what it is that you're looking at. So I like this kind of optimization where it's based on very well-defined rules and it's not just a bunch of arbitrary fiddling around to find the kind of thing that Hotspot can optimize and cannot optimize, which is very fragile. This type of thing seems to me it's much easier to reason about. It's much easier to transform back to some other kind of situation. All right. So that is the example. Now I want to talk a little bit about free structures, type classes, and then we'll talk finally about the tagless final and free stuff. So let's have a look at the monad type class as implemented in cats. I've removed the tailrec_m method because I don't think it's particularly important to this discussion. Otherwise, this is basically it. And when you look at this, I'm sure all of you go, oh my goodness, that's a church encoding, right? Because it is. Look at it again. It's got a bunch of methods. It looks very much like a church encoding to me. But a church encoding of what is the question? So of course, we can apply our inverse of the church encoding, the reification, and that would take us back to something that looks like this. And this particular something is, in fact, the free monad. Now, if you look inside cats or Scala Z, you will not see this written exactly like this. They have a different implementation because there's optimization that's gone into it. But this is nonetheless the valid implementation of the free monad. So, big idea here is that type classes are church encodings of the corresponding free structures, or putting it another way, because we're more used to dealing with type classes, the free structures like the free monad and the free applicative and the free monoid, if you're interested in that thing, are just reifications of the type classes. So we can understand a little bit about why we have these type class features in kind of functional languages, because they get that extensibility along that different axis, which we don't have in typical FP code. And we can understand more about what free structures, free monads, free applicatives are. They're just basically representing these things as data structures, which allows us to then walk over them and choose what we're going to do. Okay, so now to finish up, I'll talk a bit about extensibility on both axes and how we can get this. So I've said that type classes are OO style, but you might be thinking, but Noel, you've lied to me. You can add new operations, which is great, we know that. For example, monad extends applicative, applicative defines a bunch of things, monad gets all those things and adds to it. So that's the OO style that we're used to. But we can also add new actions. So for example, monoid. Monoid is basically things that you can add up. You can define many instances of monoid for, say, integer. You can add up integers with addition. You can also add them up with multiplication. You can take the max and a few other things. So it seems like we actually have both axes of extensibility going on here in type classes. So that's interesting. So the question is, did I lie to you? Is all of my talk nonsense? Throw it away. No, it's all right. If you remember the code we looked at before, I said we were using very classical techniques. And what we've done in the monad is actually snuck in a little extra degree of abstraction that allows us to change things along a different axis. And that is putting this type parameter up the top, basically. And if we take calculator, we can apply the same trick to it. So in our previous version of calculator, I said the return type was fixed, the return type was double. If we abstract over that return type, pull it out into a type parameter, we get something that looks like this. And now we can easily add new actions. You will notice it's a little bit funny. Now we have add of just A and A, but it allows us to add new actions. So for example, here's a pretty printer. Now says calculate of a string, and it's going to go and work. It just works. It calculates strings, pretty printing them. And the critical thing when you use this is you want to delay the choice of action. Remember, delaying actions is all about avoiding side effects. That's important. And you write code something like this. You can pretty it up with implicit methods and so on, but this is the basic idea. You have some kind of expression now, but it's parameterized by a particular calculator instance. And when you decide, do I want a pretty print? Do I want to actually calculate the result? Do I want to use a big decimal? Do I want to use double? What is it you want to do? You supply that calculator instance in here, the pretty printer, and you get back the result of the type that you want. So you can now get that extensibility. So what we've done, we've separated the operations from actions, style, I shouldn't say style. And this is known in the FP literature as tagless final style, sometimes finally tagless style, and it's known in the OO literature as object algebras. So this gives us extensibility in both directions. We can add new actions like we've seen, the thing we couldn't do before, like our pretty printing, and of course we can add new operations using good old OO inheritance. Okay. So the question that then comes to mind is, well, can we do the same thing in FP style? And yes, we can. If we reify our tagless final side to make the right kind of transformation, we would basically end up with things like the free Maana which are using these co-product or inject type classes to achieve the same effect, sometimes known as data type a la carte. It's a paper that had these. So essentially, tagless final is a church encoding of the data types a la carte, or data types a la carte is a reification of the church tagless final implementation. So again, we can relate these two different ways of writing interpreters that a lot of people are talking about right now as really just being different realizations of the same concept. And I think that's very useful. So let's have a summary. I claimed I was going to show that FP and OO make different trade-offs. I hopefully have shown you that. FP allows us to add FP allows us to add actions, OO allows us to add operations, but not vice versa. So we have extensibility in different directions, which is useful. I want to show that OO and FP are related by the church encoding, and we have seen examples of that. We've seen the transform. And this is what we have, church encoding to go from FP to OO, reification to go back. Sometimes you see other names of this. I think functionalization, defunctionalization might be. Excuse me. This relationship allows one consistent model. Hopefully I've convinced you of this because you can transform between the two. You can think of a code as existing in some kind of abstract sense, and then you choose the actual implementation which suits the extensibility needs you have in your model. This is actually useful. It's not just theoretical stuff. And yes, it was actually useful for us in achieving the performance goals we needed for this particular system. In this case, by avoiding some allocation that we got in the FP style. And finally, we can unify free and tagless final by using these ideas. Okay. So further reading, if you're interested, a bunch of papers, following domain-specific languages, very nice paper, and then some things on the object algebras and tagless final. Okay, thank you. So if you have any questions, welcome them.
In your case study, when you transformed the code by using church encoding, was that transformation done manually or automatically?
Right. It was done manually. It's the kind of thing that could be done automatically, but I guess the tooling is not here at this point. It'd be great to have tooling that allowed these kind of transforms to be applied automatically, but I guess it's not my area. It's not something I'm invested in, and it seems like something that would require quite a bit of work to cover the full complexity of Scala to achieve. So yeah, it has to be done manually, unfortunately.
Hi, thanks for the talk. So you essentially moved the streaming system from an initial encoding with free or whatever to a final one, so basically functions. So but I thought one of the reasons why we tend to use free monods more when streaming is because now you need to deal with stack safety. So now you've got functions, right, and they might not be stack safe. So did you have that problem? And if so, how did you solve that? Because I think FS2 picked an initial one essentially because of stack safety.
Yeah. Okay. So you're right. You can blow the stack in either case. If you make those calls saying give me data, those, if they're deep enough, you can blow the stack. And the same, we're just adding more calls by calling these receivers rather than returning results. So there are stack safety issues in either situation, and you can avoid them with the usual tricks of trampolining and essentially continuation passing style transformation is what you do. We did not bother for this system because queries, the kind of queries in our DAGs, our direct acyclic graphs, are normally quite short. It'd be very unusual to get things that are like 1,000 nodes deep, which we need to blow the stack. So it's not something we were concerned with in this system. It is, but it's definitely right. It is a problem that can arise, but it can arise in either situation, and you have to take steps to avoid it, either by using like the flat map, stack safe flat map, which you get in the free monad, or you have to do the same kind of things in your tagless final system of basically going through, making your calls through some kind of trampoline.
In the change that you made for that company, you showed us the church encoding where we were using interfaces or callbacks. How would using futures or something that is something like that, like futures or tasks to represent a synchronous callback and then the future on success or something like that be different in the theoretical concept of whatever you presented?
Right. I think, if I'm understanding correctly, I think using a future would still incur the cost of allocation, per element allocation, if I'm understanding correctly what you're suggesting. The sort of alternative might be like to have instead of having callbacks and having the push-pull, so it's kind of like you pull data and then again it gets pushed back up on these receivers, you could have like just a push-based system. And the problem you get with push-based systems is getting synchronous. So we have time series, they need to be aligned, they need to arrive at the same time at certain points, and that's difficult to achieve with push-based systems getting kind of synchronized across multiple inputs. So you need to introduce that. If you achieve that, you need to introduce control flow in some ways. So I'm not sure it would give us much benefit, to be honest, just going for a pure push-based system. So yeah, I don't see immediately what you're suggesting. I don't see immediately how that would benefit us in reducing allocation or otherwise, but I may be misinterpreting.
Right. I did not want to see the benefits for the allocation problem, but I wanted to understand how it fit in with the overall FP versus OO,
Right.
that they are connected through church encoding or reification.
Okay.
So
right.
yeah, I was wondering where does the use of futures sit between these two or three ideas?
Oh, okay, sorry. So I've completely misunderstood your question. Right, so yes, you can see a future. If you have a continuation passing system, or written basically a bunch of callbacks, you can see as using futures as a way of transforming that back from this CPS, continuation passing style, callback-based system back into what's called direct style, where you don't have these callbacks. So I would see future as it is both. So future is a reification of callback-based system into a sort of FP style, and it also gives you that transformation of the control flow from CPS back to direct style. So I believe they're related in that way. Does that answer you're asking? Okay, great. Okay, guess we're all done. Thank you very much again for your attention.